okay, on equilibrium. Now in this video, as I earlier said, we're going to be discussing about the equilibrium constants, okay, Kc, right, and Kp. Now one very important thing about Kc and Kp is that it leads us to what we call the equilibrium law, okay, the law of equilibrium. Okay, so let's consider our same reaction that we had in the previous video. So we have Na plus Nb in a reversible fashion to give us, let's say, Pc plus Qd. Okay, so now Kc, alright, can be given as the concentration of C to the power P times the concentration of Z to the power Q on the concentration of A to the power M times the concentration of B to the power N. Okay, so this is how you express the equilibrium constant. But when you express it like this, it makes it easier for you to be able to state the equilibrium law. Okay, the equilibrium law states that the concentration, the product of the concentration of the products, okay, the products, so meaning multiplication, the product of the concentration of the products, each raised to its stoichiometric coefficient, meaning that before you write the equilibrium or before you define the equilibrium law or you write an expression for the equilibrium constant, the reactions to a stoichiometric reaction, that means that it should be a balanced equation. Okay, so the product of the concentration of the products, each raised to its stoichiometric coefficient, okay, that's the coefficient with which you use to balance it in a reaction, okay, divided by the product of the concentration of the reactants, okay, each raised to its stoichiometric coefficient is a constant at a particular temperature, okay. So in order to tell you that Kc depends on temperature, as we said in the previous video, so Kc depends on temperature. Okay, Kc depends on temperature, right? So if you increase temperature for an exothermic reaction, you decrease Kc. If you increase temperature for an endothermic reaction, you're going to increase Kc. Okay. Now, for a reaction which is in a gaseous phase, okay, for a reaction in a gaseous phase, you consider what we call the Kp. Okay, the Kp is going to be talking about, that's the equilibrium constant for gaseous systems, right? In putting in consideration their partial pressures. Okay, so here you're going to be having, for example, let's say if I have hydrogen gas plus iodine gas, okay, combining to give hydrogen iodide, okay, so a gas. So by write that, okay, see, this is a gaseous system, and of course the reaction is exothermic, okay, meaning that it's going to release a lot of heat. Now, if I want to write the expression for the Kp, okay, I use the partial pressure. Okay, I'm going to use the partial pressure of hydrogen iodide, or of the product. Okay, now since it has a stoichiometric coefficient of 2, okay, I'm going to square its partial pressure by 2. All right, I'm going to square the partial pressure. Sorry. Okay, here I'm going to have hydrogen, partial pressure of hydrogen, right, gas times the partial pressure of hydrogen gas. Okay, so that is the equilibrium constant for a gaseous system. So that's how you express it, by using the partial pressures. And these partial pressures can either be measured in atmosphere, you can either measure the partial pressure in atmosphere, or you can measure it in Newton per meter squared, right? Depending. Okay, Pascal, remember Pascal is the same as Newton per meter squared. Okay, so that is how you express Kc or Kp given the type of reaction. Now, what is the relationship between Kc and Kp? All right. So remember that we usually have the molar gas equation. Okay, PV equal to nRT, and if you divide both sides by the volume, okay, so you have P equal to nRT over volume. But remember, number of moles, okay, by the volume is equal to concentration. So you can still write the pressure here as the concentration, okay, times the concentration, because number of moles on volume gives you concentration times the R rating. Okay. Now, if you want to continue proving, okay, you're going to have something at the end, alright, which gives you a relationship between Kc and Kp. So Kp can be written as Kc, okay, times the molar gas constant, okay, times the temperature in Kelvin, alright, divided by raised to the power delta n, where delta n is the difference in the number of moles between reactants and products. Okay, so that is it for the Kc, okay, the Kp, and the relationship between Kp and Kc. Alright, so and with this video we have come to the end of chemical equilibrium. In the next video we are going to be discussing about the other types of equilibrium, okay, the ionic equilibrium and the others. Thank you very much for watching.